Module 10, Section 8.1, Sample Spaces, Events and Probability. Objectives. Objective 1, define random experiment, sample space and events. Objective 2, understand probability, rules of probabilities and calculate probabilities of simple events. Objective 3, understand general addition rule and compute probability of an event using general addition rule. And Objective 4, understand complement of an event and compute probability of an event using the complement rule. A random experiment is a process or activity which produces a number of possible outcomes. The outcomes cannot be predicted with absolute certainty. For example, if you flip a coin, the possible outcomes are head or tail. It is a random experiment. If you roll two dice and observe the sum of the points on the top faces, it is also a random experiment. The sample space of a random experiment is the collection of all possible outcomes. An event is any collection of outcomes from a random experiment. An event may consist of one outcome or more than one outcome. Let's look at an example. A probability experiment consists of rolling a single fair die. Identify the outcomes of the experiment, determine the sample space, and define the event E equal to roll an even number. The outcomes from rolling a single die are rolling a 1, rolling a 2, and so on. So the sample space will consist of the set 1, 2, 3, 4, 5, and 6. There are 6 outcomes for this experiment. If we define the event E as rolling an even number, the event E will consist of the 3 numbers 2, 4, and 6. Rules of probabilities. The probability of an event E is denoted by P of E. P of E is always between 0 and 1, including 0 and 1. The sum of the probabilities of all outcomes must equal 1. So that means if we add the probabilities of all the outcomes of the sample space, then we will get the total equal to 1. Probability model. A probability model is the possible outcomes of a probability experiment and the probability of each outcome. The probability model must satisfy rules 1 and 2 of the rules of probabilities. That means the probability should be between 0 and 1, and the probability of all the outcomes together should add to 1. In a bag of M&M plain candies, the colors of the candies can be yellow, brown, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. If we record the color of the candy selected and assign the probabilities for getting that particular color, we will get a table like this. This is a probability model because the total is going to be equal to 1. Total probability is equal to 1, and each of the probability numbers are between 0 and 1. There are 2 basic approaches to assigning probabilities to events. One is called the theoretical method, the other one is called the empirical method. Theoretical method uses basic assumptions and a reasoning process. The empirical probability is determined by experimentation. We assign probabilities to events based on the results of actual experiments. Theoretical method of computing probabilities does not require that a probability experiment actually be performed. Rather, we use counting techniques to determine the probability of an event. The theoretical method of computing probabilities requires equally likely outcomes. An experiment is said to have equally likely outcomes when each outcome has the same probability of occurring. For example, in throwing a fair die once, each of the 6 outcomes in the sample space, namely 1, 2, 3, 4, 5, 6, has an equal chance of occurring. Computing probability using the theoretical method. If an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E, written as P of E, is m divided by n. That means the probability of E is the number of outcomes in E divided by the number of outcomes in the sample space. So we can have this formula here, P of E equal to N of E divided by N of S. Here is another example. Toss 2 coins and find the probability of at least one head appearing. When we toss 2 coins, the sample space will be these 4 outcomes. And the event E, at least one head, means either one head or 2 heads. So we have the 3 possibilities here. Head on the first coin, head on the second coin, head on the first coin, tail on the second one, tail on the first coin, head on the second one. So according to our formula, probability of E will be number of elements of E divided by number of elements of S. So we get that number to be 3 over 4. In the next example, we find the probability of a sum of 7 when 2 dice are rolled. Sample space will consist of these 36 outcomes. So that means the first die will have 6 possibilities, second die will have 6 possibilities, and using the multiplication principle we will get 6 times 6 equal to 36 possible outcomes. An outcome, something like 4, 3, is interpreted as 4 showing up on the first die, 3 showing up on the second die. To get a sum equal to 7, we need to have the event E consisting of these outcomes: 1, 6, 6, 1, 2, 5, 5, 2, 4, 3, and 3, 4. So the probability of E, P of E, will be 6 out of 36, which will be 1 by 6. Another example, a cooler at a picnic contains 100 cans of soda covered by ice. There are 35 cans of cola, 42 cans of orange soda, 15 cans of ginger ale, and 8 cans of root beer. The cans are all of the same size and shape. If one can is selected at random from the cooler, determine the probability that the soda selected is root beer, ginger ale, or orange soda. So we are going to define the event E to be selecting a root beer, ginger ale, or orange soda. And there are 65 cans of this type, adding 42, 15, and 8. And according to the probability formula, probability of E will be number of outcomes in E divided by number of outcomes in the sample space. So which will be 65 divided with, there are 100 cans, so that will be the denominator here, divided by 100. So the probability of E becomes 0.65. Empirical probability. If we conduct an experiment n times and event E occurs with a frequency f, then the ratio f over n is called the relative frequency or approximate empirical probability of the event E. Union and intersection of events. If A and B are 2 events in a sample space S, then the union of A and B and the intersection of A and B are their set unions and set intersections. For example, A union B is the event consisting of outcomes that lies in A or in B. Just like that, the intersection of A and B is an event which consists of outcomes that lies in both A and B. Number of outcomes in the union. We already know this counting formula for the union. Number of elements of A union B is the same as number of elements in A plus number of elements in B, subtract the number of elements in the intersection. If we divide this with the number of elements in the sample space on both sides, we can convert this counting formula into a probability formula. Probability of A union B equal to probability of A plus probability of B minus probability of the intersection of A and B. Here is an example. We have a standard deck of cards and we need to find the probability that the card is a jack or club. So use a Venn diagram here. So we have 2 sets, set of jacks and set of clubs, and they intersect at just one point, which is the jack of clubs. If we put the numbers here, probability of J or C is the same as J union C. This is another way of writing that. Jack or club will be the probability of jacks, which will be 4 out of 52. Probability of getting a club, that will be 13 over 52. Then minus probability of J and C. J and C is like J intersection C. So that probability is 1 out of 52. So we get the answer to be 4 divided by 13. So that is the probability of getting a jack or a club from a standard deck of cards. Addition rule for mutually exclusive events. Two events are mutually exclusive or disjoint if they have no outcomes in common. So that means the intersection is an empty set. So the probability formula will become probability of A union B equal to probability of A plus probability of B if the events are mutually exclusive. An example for mutually exclusive events. A single card is drawn from a deck of cards. Find the probability that the card is a king or a queen. If we denote the two sets, we find that they don't intersect, so they are mutually exclusive events. So the probability is going to be adding the probability of getting a king, which is 4 out of 52, and adding the probability of drawing a queen, which is 4 out of 52. Intersection is empty, so subtract 0. So we get 2 out of 13. A single card is drawn from a standard 52 card deck. Let D be the event that the card drawn is a spade, and let F be the event that the card drawn is a face card. What is the probability of the event D and F, or D intersection F? So probability of D intersection F is equal to number of elements of D intersection F divided by number of elements of the sample space. So there are 52 cards, so number of elements in the sample space will be 52. D intersection F will be a face card and a diamond. So we know that there are 3 face cards that are diamonds, so the numerator will be 3. So the answer will be 3 over 52. Next example, a card is drawn from well-shuffled deck of 52 cards. Find the probability that the card is a black card or a 5. So we can take the two sets as B equal to card drawn is black, which is event 1, and F equal to card drawn is a 5, that is the second event. And if we use the Venn diagram, we will get there are 26 black cards, 2 of which are marked as 5. So we will be splitting this as 24 and 2. 2 coming in the set F. And there are 2 more 5s. So this Venn diagram actually gives the counting here. Number of elements of black or a 5 will be adding all these 3 numbers, 24 plus 2 plus 2 equal to 28. So the probability is going to be equal to 28 over 52 or 7 over 13. An experiment consists of dealing 8 cards from a 52 card deck. What is the probability of being dealt 8 cards? So we are going to take E as dealing 8 cards. So this time we need to use the combination. That means how many ways we can select 8 cards from a standard deck of 52 cards. So that will be the number C52, 8. Combination of 52 cards taking 8 at a time. So this number will be the count of the sample space. And the number of elements of E is equal to the combination of 13 hearts taken 8 at a time. So it will be C13, 8. So the probability will be the ratio of these two numbers, C13, 8 divided by C52, 8. Once we use the calculator to compute the combinations, we get these two numbers. Dividing with that, we will get this decimal form. Next example, A small combination lock on a suitcase has two wheels, each labeled with the 10 digits from 0 to 9. If an opening combination is a particular sequence of 2 digits with no repeats, what is the probability of a person guessing the right combination? So we need to find how many possibilities are there. So the first digit can be any of the 10 digits. Because we are not allowed to repeat the same digit, the second digit can only be any of the remaining 9 digits. So using the multiplication principle, we will get 10 times 9 equal to 90 possibilities. Only one out of this 90 will be the correct code to open the suitcase. So the probability of someone randomly guessing the correct combination will be 1 out of 90. A university conducted a survey of 375 undergraduate students regarding satisfaction with student government. Results of the survey are shown in the table by class rank. If a survey participant is selected at random, what is the probability that he or she is satisfied or is a junior? So the event is satisfied or is a junior. So we can take yes for the event of the student being satisfied, J being the event of the student being a junior. So we have the number of outcomes in yes will be the addition of all those numbers, which is 233. The number of outcomes in J will be the addition of this column here, which will be 98. And they do overlap at 67. So that is the intersection count. Satisfied and junior will be 67. Now we can use the probability formula. Probability of the union equal to probability of S plus probability of J minus the probability of the intersection. So when we put the numbers, notice that the sample space will be containing 375 students. So denominator will be 375. So this S here is not the sample space, that is the event that a student be satisfied. Next example, refer to the given Venn diagram for the events A and B in an equally likely sample space. Find the probability of A union B. Probability of A union B is equal to number of elements of A union B divided with number of elements of the sample space. So in this Venn diagram, U stands for the sample space, and the sample space will contain a total of 100 outcomes, which is adding 45, 15, 25 and 15. So when we do this one, we will get number of elements in A union B is 85, that is adding these three numbers. So that will be 85. So 85 divided by 100 is the answer. Complement of an event. Let S denote the sample space of a probability experiment and let E denote an event. The complement of E denoted by E prime is all outcomes in the sample space that are not outcomes in the event E. So to calculate the probability of the complement, we can subtract the probability of the event E from 1. So probability of E complement is equal to 1 minus probability of E. So here is an example. Suppose that blinking causes a person's eyes to be closed to 2% of the time. If a photographer takes a picture of 3 people, what is the probability that all 3 people will have their eyes open? So this says that person's eyes to be closed has got a probability of 2% or 0.02. So the complement probability will be 98% or equal to 0.98. So the person keeping the eyes opened will be 0.98. We have 3 people, so we need to actually multiply the probabilities. So person 1, person 2, person 3. So probability here is 0.98, keeping the eyes open, 0.98 and 0.98. So this is person 1 person 2, person 3. So all three, keeping the eyes open, will be having a probability 0.98 multiplied with 0.98 multiplied with 0.98. So that number is going to be